Welcome everyone. Last time we saw the recipe that is used to solve any machine learning problem, and we cast the problem as that of distribution estimation, and depending upon what distribution we estimate, we give different nomenclatures to those problems, and I also gave you a recipe where you are given samples from the distribution, assume a parametric model to the underlying unknown distribution, compute a distributional divergence metric, estimate it using samples, and optimize it over the parameter space. Okay, and we also saw an example at the end of the class for one particular problem of supervised regression, where x is in RD and y, the label, is in the space of real numbers, and data are samples of this sort. We have xi comma yi. We have n samples that are drawn IID from an unknown underlying distribution Pxy. See, in fact, when I say that there is an unknown underlying distribution, it's technically wrong because there are n distributions that are identically distributed. Or there is one distribution. I mean, you know the the analogy. Now, the problem was to estimate the posterior of y given x, the labels given the so-called input random variable x, and we walk through the recipe that we had seen. So, we assume p theta, which is the model distribution which we want to estimate. This is one example that I showed you where we assume that to be a Gaussian distribution. The distribution is over y, and we represent the mean of that distribution using a canonical function h theta of x, where h theta is a function from x to r. In general, it is from x to y. And we cast the problem of minimizing the KL divergence or maximizing the likelihood, and saw that it boils down to finding the parameters theta by solving this well-known problem of minimizing the least square error. Okay, that's what we saw. This was an example. In today's lecture, what I will do is I will walk you through an alternative route, meaning we will start by casting the machine learning problem as the one of minimizing what is known as the risk function. Okay, and then we will see that minimizing or optimizing the risk function is not tractable in practice. So, we resort to minimizing the surrogate loss function or surrogate function, which is called the empirical risk. Okay, and I will show you that minimizing empirical risk is equivalent to estimating the distribution. So, whatever we have formulated so far, I will show you that there is an alternative formulation to this problem, and I mean, one can look at the problem from both ways. In literature, some people choose to look at the problem as distributional estimation, and some people choose to look at it as empirical risk minimization, but both of them are solving the exact same problem when they are solved in algorithmic way. So, that is the content for this in today's class. From the next class onwards, I will not make this distinction that we are doing ERM or we are doing maximum likelihood estimation. You should be in a position to understand that both of these are exactly the same. Okay, at times some algorithms are formulated as ERM, some other times algorithms are formulated as distributional estimation. Okay, and you have to appreciate that both of them are exactly the same problem, done in two different ways. Okay, so let us look at the risk minimization framework. I will do this for supervised learning, where we assume that we have a data space and a label space y, and this can be extended to the other cases as well, as we will see in a while. So, the problem setting is as follows. We are given the same data, which is a set of tuples of this sort. We have xi comma yi 1 through n, and this is drawn IID from an unknown underlying distribution Pxy. This is the starting point, and in general x is in Rd and y is in Rk, or it can also be a discrete set. So, depending upon what set you are operating on, the problems are called the regression or classification problems, and you know that. So, we are looking at supervised learning because there is a label set onto it, but this framework is generalizable to the so called unsupervised learning as well, which as we will see. Okay. The goal is the following. Goal is to estimate a hypothesis function. So this h, which is a function h that operates on x and maps to y. Okay. There exists a function called hypothesis function that takes elements of x and maps it to y. That is what we define hypothesis function as that sort. Now, goal is to estimate a hypothesis function. So, this h, okay, belongs to a class of hypothesis set. So, there can exist infinite functions, right. So, this is set of all functions from x to y. So, given that there are infinite ways to map two sets, right, x to y, so we need one particular hypothesis that we choose from. So, how do we choose which is a good hypothesis is the question. So, what do we have? All that we have is the training data D or the data set D. Now, how do we define? So, we will have to come up with some goodness measure, okay, that would tell me whether a given h is good or bad. Okay. To do that, so let me write that. So, quantify the goodness of an h. So, given a hypothesis function, okay. So, this function, this is a function of x, right, as you can see it is a function of x. So, we have to quantify the goodness of this particular hypothesis, which is nothing but a function from x to y. So, how do we do that? Now, define a notion of loss function. Loss function L. Now, this loss function is a function that operates on the cross product of y and y, and it will give you a positive real number. This is the definition of a loss function. So, what do I mean by that? So, this loss function can take the values from the spaces of y, the cross product of y with itself, and then give you a positive real number. Okay. So, any function that operates on the cross product of y and gives you a positive real number is a loss function. Okay. Now, an example can be this, right, it takes h of x and y as input and it will give you r plus at the output. H of x is also in the space of y. Why? Because the range or codomain of this h of x is y. So, it is a valid function. So, let us take an example of this loss function. Example of this loss function can be, so it takes h of x and y, and this can be equal to, assuming that both of them are vectors, simply be the 2 norm of the difference between these two. Okay. This is called the squared error loss, and another example can be 0 if these two match and 1 if they do not, right. This has a name, does anyone know? This is called the 0-1 loss. Okay. This is a design parameter, one can choose what loss function one would want to operate with. Okay. I have just given you 2 examples, there can be many more, we will see more examples of this loss function in this course. Is this clear? So, it is simply a function that operates on the cross product of y and gives you a positive real number or non-negative real number, it can also have 0 of course, right. And these are a couple of examples. Okay. Now remember what our goal was. Our goal was to estimate or come up with a hypothesis function that operates on x and y, and we wanted to do it by using the underlying data set and come up with a good hypothesis. So we wanted to quantify goodness. What is a good hypothesis? To do that, we defined the notion of a loss function. But note that a loss function operates on a single pair of data. So it takes one hx, one y and gives you a number. But we cannot define objectives only by looking at one particular sample, right? We have capital N number of samples, and we need to aggregate the loss on all those samples. And how do we do this? We take an expectation. Okay, so let us define extending the loss function on the entire data set. For the population. So define what is called as a risk function, which is the expected value of the loss function where the expectation is taken over the joint distribution of x and y. Okay, this is called the risk function. Okay, now we can define the problem of the primary problem of machine learning, which is estimate goal problem. Estimate h star of x, which is given as the function that minimizes this expected loss or minimizes the risk, expected loss over the joint distribution, and this optimization is for all h that is in the hypothesis space. So amongst all possible functions that can map x to y, give me the one that minimizes the expected loss, and the expectation is taken over the joint distribution of the random variables that we have. Does that make sense? See, this formulation is what is famously referred to as the risk minimization framework. Okay, what are you doing is trying to find a hypothesis that would minimize the risk function. What is the risk function? It is the expected value of the loss function. That's the story. Okay, okay, so far so good. You will be surprised to know that this problem is exactly the same problem as that of estimating the distribution. We will show that in a while. They are mathematically equivalent. Okay. Now look at the problem, right? The issue is, can we solve this optimization problem? Again not, because we do not know the underlying distribution. So the exact risk minimization problem cannot be solved. So what do? You resort to solving a surrogate or an alternative where risk, okay, let me call it, it's actually called the true risk in the literature. True risk function cannot be minimized since the underlying distribution pxy is unknown. Okay, therefore consider a surrogate. So define what is called as the empirical risk r hat of h, which is defined as sample mean version of the true risk. Okay, this is what is called as the empirical risk. Okay, so finding out H cap star as the minimizer of empirical risk is the problem that we actually solve in practice. So, this problem is referred to as the empirical risk minimization or ERM. Okay, so true risk cannot be computed. Of course, here we have to write that your xi and yi are being sampled IID from pxy. Of course, I mean you have that. Otherwise, statistics do not guarantee that these are equivalent, right? So, you will have to do that. So, this is called empirical risk minimization. So, from an algorithmic standpoint, what do? You compute the loss function on all the data points, take an average and find an edge that minimizes that. Okay, this is empirical risk minimization. In fact, the machine learning 101 courses that you find online actually starts from this equation: define a loss function, compute the average and minimize. Correct? So, this is what empirical risk minimization is. So, now the central question that is that occurs in machine learning is, so we know from statistics, right? So, we know that R cap H, the empirical risk, converges to true risk, correct? Why? This is simply law of large numbers. The sample mean converges to true expectation if you have a large number of samples, okay, and they are drawn IID, this we know. But this is not important. See, what is this saying? This is saying that I have to solve an optimization problem over some objective function, correct? Now, I cannot compute this objective function. Now, what am I doing? I am considering a surrogate objective function, and theory is telling me that this objective function converges to the true objective function if I have infinite samples. That means nothing to us. Why? What are we actually interested in is, we are interested in the convergence of the minimizer of the true risk to the minimizer of the empirical risk. I am not guaranteeing anything on that. I am only saying that empirical risk converges to true risk. Fine. I am not saying that the minimizer of the empirical risk converges to the minimizer of the true risk. So, that is the central question in machine learning, right? So, you have to design an algorithm, however, H star of x, which is the minimizer of the true risk, okay, may not converge to H star cap of x, which is the minimizer of true risk, okay. So, the central question when would H when would H star hat x converge to H star x. So, this is the central question that is asked that should be asked while you are designing any machine learning algorithm. Okay, this is also called the question of generalization. So, we will see more on this as we move on in the course. So, you might have heard about these terms, right? Overfitting, underfitting and so on. This is exactly where it comes from. So, the question that we are asking is whether or not the minimizer of the empirical risk converges to the minimizer of true risk or not. See, mind you, we do not have access to H star of x at all. Okay, we do not even know what the true risk is. Then the question is, how do you even try to answer this question? How do you even know whether the minimizer of true risk minimizer of empirical risk is any closed minimizer of true risk. Okay, we'll take up those questions. There's an entire sub branch in machine learning called statistical learning theory that deals with only this question. So basically, people come up with an algorithm. What is an algorithm, by the way? Any machine learning algorithm is a way to solve this optimization problem. All machine learning algorithms is to, again, if I have to give a recipe to do ERM, what should we do? So we'll have to choose an edge or a class of families of edge, and then we have to choose a loss function and solve this optimization problem. Exactly the same as choosing a model for p theta or pxy, and then choose define a divergence metric and then solve the optimization problem. Same thing will happen. Now that's an algorithm. Once in the historically, when people come up with a particular algorithm, they would always come up with a bound on does there exist an upper bound, okay, on the empirical risk in terms of true risk. The question that they are asking is, can I give you a guarantee that if you run my algorithm on a particular data set, okay, then it is guaranteed that as long as your data is coming from the true distribution, can I guarantee performance? See, that's the question that I am asking. If you look at it, what does this question translate to? The question that I am asking is, I have seen one small sample of the entire distribution and I have built an algorithm on that. Suppose I take a different sample from the underlying distribution and use the same hypothesis function to predict what would be the average risk that I get when I do that. Now, if I would have optimized, or the closer I am to h star of x, the minimizer of the true risk, the better my performance will be on unseen data. Do you agree? That's the goal. See, the goal is, how do you construct an algorithm, okay, so that the minimizer of the empirical risk is close to the minimizer of the true risk. What can you say about the algorithm that you have constructed? There's a lot of theory on in fact, you might have heard about this particular machine learning algorithm called support vector machines, SVMs. It was extremely popular in one point in time because the true risk of an SVM could be very well upper bounded actually in terms of number of samples in the data set and number of parameters in the model. Okay, that's why SVM was extremely powerful, but unfortunately in today's scenario of extremely huge models with billions of parameters, it is very hard to come up with these kinds of generalization bounds. These are called generalization bounds. But the question that is being answered is, how far is the minimizer of the empirical risk to the minimizer of true risk? But if your sample set or the data set itself has all possible samples that you can look at from the distribution, then there is no point in asking the question of generalization. Perhaps that's what is happening, because I keep saying this, right? If you solve ERM on the entire universe, then you don't even have to ask this question because you have all samples that you can see. Right? That's the point. So today's models, for instance, these GPTs, etc., they actually solve this problem. Algorithmically, what is solved is ERM, okay, but the question of convergence is not asked because we still do not have enough mathematical tools to bound the generalization error for models that have so many number of parameters and compositional in nature. So there's no theory yet that is developed, but again, empirical risk minimization is working today. I mean, working empirically because the number of samples that we are training our models on is too huge. Question? Yeah.
So for example, when you said for models as big as LLMs, right, where they have like 700 billion parameters, right, and there is no way to know what is the true minimization function, then how do you, like, where do you stop at while training those?
Good question. The question is, when you are solving this optimization problem, how do you stop? How do you decide where to stop, when to stop? Hold on to that question. In a few classes, we will look at this thing called the bias variance decomposition and so on. So when I give you insights on when to stop training and how do you do ERM and so on. Okay. So basically what is done is, you divide your data set into two subparts, right, training and testing. Okay, so you train it on trained data set and test it on a subset of your data, and if it does good on this test set, then you stop your training there. Very broadly, but we will formalize all these notions as we move on. Okay. Okay, it's there. Okay, now let's look at an example of how to do empirical risk minimization. Okay, and then we will move on. For example of ERM. For a regression problem. So given data, we have the exact same setting as before. We are given data, so we have x that's in RD, and we have y that's in R. Let's take univariate regression now. Now suppose h theta of x comes from a family of parametric functions. Parametric functions parameterized by theta. Okay. Now examples can be that your h theta of x can be, let's say, theta transpose x, or it can be some e power theta transpose x, and so on. I mean, you choose a function. So what sort of function should we have to choose is a design choice. This is actually called a model. We will see that in a while. Now define a loss function, or rather choose a loss function. Let's choose, let's say, a mean squared error. Then compute the empirical risk. Empirical risk is 1 over n is from 1 to n. We have h theta of x minus xi minus yi. These are scalars, right? So I can do this, right? And find theta star as the minimizer of this empirical risk, and you minimize over the parameters theta. So if you note, this is exactly the problem that we were solving. So this is equivalent to estimating the conditional distribution. So let me write that. The above is equivalent to estimating p theta of y given x using the maximum likelihood or ML estimation with an assumption that p theta of y given x is Gaussian with mean h theta of x and variance I. So this is the equivalence, meaning if you solve empirical risk minimization, okay, then you are estimating some distribution. So in this case it happens to be the conditional distribution with a distributional assumption on that particular distribution, and the parameters of that distribution so will be the same as your hypothesis function. So that is the equivalence. So whenever you solve, see sometimes what happens is we don't, why do we need these two alternative explanations is for the following reason. Sometimes what we do is we don't explicitly define the distribution, the underlying distribution, and do a maximum likelihood estimation. Rather define a loss function, okay, and solve ERM. But we should always remember that there exists some distribution, okay, that corresponds to solving this particular problem. So we may not know what that distribution is, and we may not even know what the underlying form for that distribution is, and we may not even care what it is. For instance, if you are building, let's say, a GPT, then this h theta is a particular type of function called transformer, okay, and the loss function that is typically used is the cross entropy. I will define it in a while, okay. I will show the equivalence of what distribution are we assuming when we do the cross entropy, but it's the loss function is called cross entropy loss function, and you solve ERM, okay. We don't look into that as maximum likelihood estimation, right, but you should know that this is what we are doing. So sometimes what happens is in cases such as, let's say, a Gaussian mixture model, we don't look into that as ERM. What we do is we explicitly define the underlying distribution and cast it as maximum likelihood estimation or minimizing KL divergence problem. And same thing would happen, let's say, for a lot of generative models. One example is that of diffusion models. You might have seen some of these commercially available image generators, right, where you can type out a textual prompt and it generates images corresponding to that, right. They are all samplers, they are all generative models, again, as I said in my next course. So when you build a generative model, you are solving the problem of minimizing KL divergence explicitly by assuming a canonical form for p theta of x, because you want to model the marginal of x and sample from it. There you don't cast it as ERM, okay, you cast the problem as that of the minimizing KL divergence by assuming some canonical form on the underlying distribution, but they are exactly the same. Got it? So any ML algorithm can be seen in two different angles. One, define a function from two random variables that you are considering, call that hypothesis, define a loss function, compute the empirical loss and solve an optimization problem on the hypothesis space and call that your model and ship it. That's one way to look at it. The other way to look at it is define a distributional functional form on the underlying distribution that you are trying to estimate, minimize the KL divergence on the parameter space of the model distribution and ship the distribution itself. When do you want to ship the distribution itself? Mostly in the case of generative models, or even in the discriminative models, we will see, right, that finally in some cases the optimal function that you need to estimate h will be a distribution, because if the problems are equivalent, then at least for some cases the solutions, or rather all cases, right, analytically you should be able to show that the solutions are equivalent. We will see that in a while. I will take an example and show you that had you solved the problem of true risk minimization, okay, then what will be your true risk minimizer is. So it turns out that the minimizer of true risk is the conditional distribution for certain cases. So estimating conditional distribution directly from data is equivalent to minimizing the true risk. So that is what we are going to see now. Okay. So these two parallelizations has to be imbibed in your head, because some people use this, some people use that, some models use this formulation, some models use that formulation, but they are exactly the same. Is that okay? Okay. So now, yeah.
You mentioned the hypothesis function is 2 transpose x, or it's linear or non-linear.
Can be anything. Can be anything. Yeah. So we will see examples of that later in the course. So this is called, if you use your h theta of x to be of this form, it's called linear regression. If you use this one, it's called logistic regression. Different choices for the hypothesis class. That's it. Okay. Okay. So now what we will see, that I just will prove the statement that I just made, that there is an equivalence in the solution space as well. Right now the equivalence was shown in the optimization space. The problem that you are solving are equivalent is what was shown. Now we will take a case and show that even the solutions that we find out from two different angles happen to be the same if you choose the parameters that way. Okay. So establishing equivalence between risk minimization and divergence minimization. Divergence minimization are also called the maximum likelihood estimation. Minimizing the negative log likelihood. Some people call it NLL as well. I have told you that, right? So let us look at this. Now, question. What function minimizes the true risk? Suppose we had access to distributions, right, all distributions. The question that I am asking is what function minimizes the true risk? Now, as you can imagine, right, depending upon the problem that we are solving, if we are solving the classification problem or regression problem, supervised, unsupervised, this function changes. Obviously, it should change. For generative models, for instance, the minimizer of the true risk, if you define the loss function that way, should be the marginal distribution, isn't it? Because we are finally estimating the marginal distribution in the case of generative models. Here it should be something else. So depending upon what problem are you trying to solve, this has a different answer. But we will see this for one particular case, which is the case of supervised learning. Okay. The question is what function minimizes the true risk. So consider the case where you have data that is pair of labels and features, okay, and we are defining the loss function as 0, 1 loss function. So I will do it for this particular case, okay, and equivalent results exist for other choices of loss function and other choices of models as well. You can take that as homework, or yeah, it's for further discussion. So the loss function that we are looking at is the 0, 1 loss function, which is that if the hypothesis matches with the actual label, then I assign 0 loss. If it does not match, I assign 1 loss. And I will also say that let us say that, okay, let me write it, make it more specific. Suppose our xi is in RD and yi is binary. This is to simply make my life simpler so that the algebra works out to be simple. So all these results can be extended to the regression case or k-class classification case. Okay, so that's your homework. I'll just formally tell you what your homework is. But yeah, so let's consider that we are solving a binary classification problem where it is diseased or non-diseased. You can always go back to that X-ray example that I have been citing, right? So disease versus non-disease. This is the, and I am operating under 0, 1 loss, 0, 1 loss function. Is that okay? Okay. Now with this, the risk function, the true risk that I am talking about is the expected value, expectation of the loss function, right? And the expectation is taken over the joint distribution of x and y. This is what it is. Okay. Now the question is, I would want to get the minimizer for this. What is the h function that would minimize this? So now if you observe it, this entire risk is a function of h. That's why I have written it as a function of h. You change the hypothesis, the risk changes, isn't it? So I can find out the minimizer for this particular risk as a function of on the space of h. So what hypothesis minimizes this? at least under these conditions where y is binary and loss is 0, 1. Let's look at that. We will stop here and continue in the next lecture.